Hi, and welcome back after the coffee break. Next up will be Felix with packaging Tensorflow for fun and profit. Have fun.
Yeah, thanks for the introduction and thanks for having me here. So before we start, who of you know what Tensorflow is? Okay, that's very good. And who of you knows that there is already a packaged version of Tensorflow in Debian? And who of you know why we had to repackage it? Okay, actually just because the version that is in Debian is simply too old, and it's way too old. Okay, so let's start. Maybe a couple of words about myself. So I'm a computer scientist. I work for Siemens. I come from the high-performance computing domain, and I also love to work with open source software. Whenever I find a bug, I try to either report it or if I'm able to patch it, and then I try to do that. I'm quite familiar with open source software, and also at Siemens we have a lot of products that use open source. And for the base system, we also have a lot of products that are based on Debian. So let's start with the background of the project, why I had to package Tensorflow. At first, we have some devices. I have one of the devices with me. That's such a box, which is ARM-based. We also have some larger IPCs, which are x86, 64-based. And inside these boxes, our customers wanted us to integrate hardware accelerators for machine learning. And there are some devices out in the market. One example here would be the Google Coral chip that's available in various form factors. And the good thing about this chip is that it's very cheap. It has a PCIe interface or can be connected via USB. And when you do machine learning with Tensorflow, then you can offload the computations from the CPU of the system onto this dedicated chip, and by that you have more CPU power available for the rest of the applications. And of course, there's also already some infrastructure from Google, so libraries to use this chip from both C and from Python. They are already Debian packaged, but unfortunately they are not really packaged the Debian way, but they just use their own build system to generate some pre-built artifacts, which you then can install on the system. But that's not what we want there. We want to have an open platform which also follows the Debian way. And by the way, where we really know what's in the packages. Another problem we had was that as I said, this box here is an ARM box, and when you compile things like TensorFlow, which take hours to compile even on powerful machines, you really want to be able to cross-build everything, because you cannot emulate the compile. That's way too slow. Okay, a couple of more things we had to consider. Software bill of materials, as I said, we really wanted to know what's in the product. We also want to be reproducible, to be sure that when we run the build 2 times, that actually the same artifacts are generated. Then we want to have the things maintainable, and that means we want to be as close as possible to upstream. Also upstream the things we fixed there, because we do not want to have a fork and have to maintain that fork forever, but instead we really want to work together with the community to so that we all profit from the work we did there. Again, this is the chip, and here what we integrated also in these systems are these tiny PCIe-based chips. And even, I can open up the box here. So if you look at the box, just this thing here is the chip where then the acceleration takes place, so where the neural networks are then executed on. And this is available as both a USB device and a PCIe device. There's a small difference. For the USB device, you don't need kernel modules, which makes the integration much easier. But for the PCIe devices, we wanted to have the kernel module packaged, and also a pre-built version of the kernel module as well as a DKMS package, so that our users can take what we give them and install that on their kernel. And as I also said, we want to use the standard Debian infrastructure with dpkg build package or dbuilder or pbuilder or sbuild or whatever, but not pre-built packages that are generated by a different tool. And another problem we ran into is that it's not good practice to fetch dependencies or download dependencies at build time from the internet. So what we wanted here is that we pre-download everything, then we have our sources archive, and then we tell the build system, please use what's in there, and just use that to do the build. Okay, now things get a bit more complicated, unfortunately, because we have to talk about the dependencies. Let's start with the dependencies of this chip. To be able to use the chip, we need the libedge TPU, which is available in various versions here, max and standard. The only difference is that max gives more power to the chip. By that, the chip gets hotter, and I think they had some product safety problems with the USB device because you can touch it. That's why they implemented two versions of the same library just to throttle the chip so that it's not getting too hot and it's still safe to touch it. But for the PCIe device, I mean, it doesn't really matter because it's in an inner case. And then we have the development libraries. We have the DKMS version of the kernel module. We also want, I mean, we work for embedded, so we don't want to have a compiler on the target normally. That's why we also want to have a package with just the pre-built kernel module for the kernel we run there. And then we have some Python bindings to use this infrastructure as well. And as you see, on this slide, there's no TensorFlow, but of course, we have transitive dependencies. By the way, the Edge TPU compiler is binary only, so we cannot really do things about. I mean, it's just required for our users so that they convert their model, their TensorFlow model, to be able to execute on this chip. But yeah, we don't have the source code for that. But anyways, we don't have it on the product because the customers bring their own model there. Okay, and here we have the first dependency to TensorFlow, because these libraries depend on TensorFlow Lite. By the way, if you think about the current existing Debian packaging of TensorFlow, it doesn't contain TensorFlow Lite. And TensorFlow Lite comes from the source package TensorFlow, so that's where the fun starts. Dependencies. If you are familiar with how TensorFlow is currently built, they don't use CMake or make or whatever, but instead Google invented their own build system, which is called bazel, which is technically incompatible with the rest of the world because all the dependencies that are used to build a component are described within the bazel rules. So you cannot simply say, please use the libraries that are on the system and the headers that are on the system, use that as a dependency and build it for that. No, bazel fetches everything from sources and also even including compilers, if you think about cross-compiling, and handle the dependencies internally. Another problem with bazel is that the versions have to fit quite closely, so you can't use a too new or a too old version for that. Of course, for the Debian way, we want to inject the system dependencies and build it with these instead of vendoring everything. And luckily, TensorFlow itself has some infrastructure for that. So they have rules where you can switch based on a parameter, TF system libs, if you want to use the system libraries or the vendored ones. But this is not possible for all system libraries, and also you manually have to specify the libraries that you want to use from the system. Another problem was cross-compilation. This was really a nightmare, but a bit more about that in 2 slides. And then bazel cache is always in home. This is also a problem when building, because home might be shared, and actually you do not want to escape the builder. So as I said in the beginning, you cannot use all system dependencies, but only the system dependencies where TensorFlow has support for that to switch over to the system. And for the others, as I said, we do not want to download them at build time, but instead we want to prefetch everything so that we have a sources archive also for reproducible builds. And that's what we do here. So we have, this is the Debian rules file, and there we have a local step which we manually call to let bazel fetch all external dependencies. And then they are placed in the cache, and then we can relocate the cache, but unfortunately we also have some symlinks in the cache which are not really relocatable. So first we have to make them relative, and then we can relocate the cache and put all that in the sources package. So that was the first fun we had there. Then the next thing is how to make sure that bazel cannot download anything at build time. And that's rather simple. I mean, we just set HTTP proxies pointing to nowhere. And by that, we at least know when the build fails, probably we just missed a dependency because then the fetching fails. Another thing we do here is to set this override repositories flag to point that to the things that are in the sources archive, because normally all that would come from the bazel cache from the home folder. But of course you cannot really put the home folder in the sources archive, and you don't want to do that. And the last thing here is that we still have to specify this variable which tells the rules which libraries should be taken from the system. Time is running. Next problem we had cross-compiling and dependencies. So as I said, we use some system dependencies that are not only, but we have a lot of Python dependencies. And there we had the problem that not all Python dependencies are packaged properly. And by that, some of the dependencies could not be installed in the before building. And the problem there was that often we saw a dependency to Python 3 all, but if you have packages that not only contain Python code, but also some native components, it's better to do it this way, because by that you make sure that the package can be cross-compiled. And I mean, for the Python package, it's not about being able to cross-compile the Python package, but we want to be able to install it as a dependency for cross-compiling TensorFlow. So that's one thing, and we upstreamed a lot of these fixes for packages that had problems there. Another problem is the cross-compilation itself. So normally when you think about CMake projects, you write a toolchain file, and I mean Debian, the deb helpers have infrastructure for that, you don't even have to write it, which contains some like 10 lines specifying the compiler, the linker, where to locate headers and sources, headers and binaries. But with bazel, the situation is a bit different. You have to also write a toolchain file, but the toolchain has to specify very precisely where the compiler looks for things, where it's allowed to access files, and so on. And by that, this toolchain file is literally 1,000 lines of code. I mean, you can reuse it across the components that you build with bazel, but it was really a hassle to create the toolchain file in the first. And finally, what you do when cross-compiling is, I mean, we simply dispatch. So this is the Debian rules again. We simply dispatch based on the deb host architecture, and add this cross tool top here, and also specify for which CPU we build. So here for ARM, we have one toolchain file, and adjusted the CPU parameter, so it works for both ARM HF and ARM 64. And then, yeah, once you do that, you should be fine, and you are able to cross-compile things. Okay, lessons learned. So we started, when starting with the packaging, we started with the version that is already packaged in Debian, which is 2.3. something. That's available on Debian Salsa. And based on that, we tried to move forward to at least version 2.5, because the Corel things only work with the version 2.5. And by that, we had to also bump TensorFlow to this version. And then while we did that, there were some CVEs detected in TensorFlow, and by that we also had to bump the minor version there. But the problem there was that even minor version changes in TensorFlow change things all over the place. So you cannot simply bump the version, but you really have to think about your packaging, rework dependencies, make sure that the versions are still compatible, and so on and so forth. So this repackaging requires some significant effort for both doing it and also testing it. Another problem is with inter-project dependencies, so other components that depend on TensorFlow, because normally they simply they use Git submodules to point to the dependencies, and of course they have a hard-coded version in it. I mean, here it's just pointing to a Git version, but by that it's very hard to do a version bump, because all the consumers of this component have to do the version bump as well, or you have to do patching. And actually, I mean, sometimes you can inject versions, but often the only way to do it is simply patch it, and by that bump the versions of the components. Coming to the outlook, I think the time is already almost over. We have still some limitations in the packaging, and that's also why it's not yet, I mean, it's open source, everything we did there, but it's not yet fully in the official Debian. At some points, we had to violate Debian policies. By that, we are still not fully SBuild compatible, so we can build the TensorFlow Lite for SBuild, but not the whole TensorFlow for that. And we also didn't put too much effort into packaging the build infrastructure itself. So we somehow just assume that we have a recent bazel version, but packaging bazel, so the build tool for that, is a whole different story, and it's also very much effort to do that. A last problem is that the maintenance of all that is a bit unclear, because we just did it once for the product, but I mean, in the end, we want to have it upstream, and then the community can adopt. Of course, it would be better to discuss some topics again with Google, to how to improve there, how to make it more distro-friendly. Then we want to have a more recent build tool chain in Debian, like the bazel infrastructure is quite outdated, which is in Debian, so that's one thing that would have to be improved to move forward with the packaging. And also to add some deb helper tooling to simplify all the things we do there, because now we have to do it for each package that uses bazel, and this creates huge rules files, and I mean, it would be better to have infrastructure for that. And I think that's it. So thanks for listening. Here are the links where you can find the infrastructure or our work. It's MIT licensed or licensed according to the projects we patched there. So it's easy to reintegrate it.
Thank you. Thank you, Felix, both for your talk and your efforts on packaging TensorFlow. Are there any questions? Questions? Okay, then thank you again, and we will have a short 2 to 4 minutes break so Agat can prepare the laptop and stuff. See you soon.